Good afternoon, ladies and gentlemen. Welcome again to the second round of breakout sessions on track 2. Without further ado, let us move to these presentations. Please note that each speaker will have a duration of 15 minutes. During the first 10 minutes, each presenter will present their experiences, and in the last 5 minutes, the floor will be open for any questions raised by the audience. If there are multiple presenters, the presenter that is called upon on stage, please introduce your fellow participants as well. Our first presenter this evening is Ransika Costa, paper ID 14, a novel approach to ingredient substitution in food recipes. He's a final year undergraduate, Department of Computer Science and Engineering at the University of Moratuwa. Ransika Costa, over to you.
So, good afternoon everyone. So, my name is Ransika Costa and this is my colleague Tevin Senath. We are from Department of Computer Science in University of Moratuwa, and our research is to find a large language model based ingredient substitution in food recipes. And this is the table of content, so I will move forward. And when talking about food, it's actually essential for our day-to-day life. And food recipe personalization is an important role because we need that because of many reasons, like there will be unavailability of certain ingredients, and some people may also have allergies and personal preferences like vegetarian or carnivore diets, and also some religious practices as well. So for this personalization, ingredient substitution plays a crucial role. And also, we can't actually blindly just substitute ingredient for another. We have to also consider the context of the recipe as well. As for this example, for frying eggs, we can use oil for a substitute for butter. But in the case of baking a cake, that's not a good substitute. So we have to consider the context of the recipe as well. So even though there are some existing approaches to address this problem, the existing approaches are actually suboptimal, or they don't have enough accuracy at the moment. And I just don't want to bore you with this motivation stuff. I'll move on. So our main objective is to find a large language model based ingredient substitution which use prompt engineering techniques to also help consider the context of the recipe before giving the substitution, and also enhance the capabilities of the LLM in the domain of food ingredient substitution. And this research paper was published by a Meta company, and they have this graph neural network ingredient substitution which use their ingredient relations to identify the similar ingredient and then provide substitute. And we use this as our baseline. So what they have done is when given some ingredients for recipe, they won't give the input as what they need to be replaced, and then the model will itself give the updated recipe ingredients along with the substitute. So these are the main two evaluation techniques that Meta use for their Gizmo, mean reciprocal rank and hit at k-score. So for k values, they have mainly used 1, 3 and 10. And this is the methodology overview of our project. So we just, when we go to here, we just get this recipe 1 million subs data set, which is actually from recipe 1 million, which is the largest available food data set in the world. And we pre-process that and give the user input and create a basic template, which is not specific for a language model, just a basic template. And then we consider these 4 contexts. So we experimented with different things. So we just gave the source ingredient, and then after that, source ingredient plus recipe title, and then source ingredient plus recipe ingredients, and finally giving all 3 at once. And we got the best results from this source ingredient plus recipe title combination, and we move along with that. And for this, we use mainly this Llama 2 Mistral and Gemma LLM models, and we do some zero-shot prompting results, and then got the best selecting prompt out of that. Then we created the fine-tuning dataset, and then perform a supervised fine-tuning, and then after fine-tuning, we do a final improvement of the fine-tuned model, and then got the evaluation. So we actually divided the workflow and evaluation into these subcategories. So we'll go through them. Talking about the datasets, the main dataset that we use for our task is called recipe 1 million subs, as I said before. So they have this tuples which contains the source ingredients, which is the ingredient we need to substitute, and then the expected substitute ingredients. So it's easy for us to understand what is this substitute ingredient for a given ingredient in a selected recipe. And in their dataset, they have unique over 6,000 ingredients, and then total ingredients is over 10,000, which means, or unique means that ingredients may have multiple names for the same ingredient. So unique ingredients we have more than 6,000. And moving on to the prompt selection, as I mentioned in the method overview, we got the best result from this source ingredient plus recipe title combination, and we got the best result from Mistral 7B, and also we tried Llama 2 as well. And when we got this actually from the instruction tuning, when we did some in-context learning by giving one-shot prompts, like giving an example before actually getting output, we got actually a low result. So moving on, these are some example prompts that we use for instruction tuning. And I would like to hand over to Tevin.
Yes, thank you, Ransika. So after selecting a prompt, the next task was to select a suitable model for our research. So for that, first we got zero-shot results with these open source language models using the selected prompt, and according to the results, we can see that by getting zero-shot results, we couldn't outperform our baseline Gizmo model. Therefore, as our next approach, we fine-tuned those LLMs. So for using supervised fine-tuning method for creating that data set, we use recipe 1 million subs data set, and we use these prompt templates to create data sets for each LLM model. And as we all know, fine-tuning LLM is a huge task, and we require massive hardware. Therefore, we use these parameter-efficient fine-tuning techniques, LoRa, QLoRa, and Galore. Then here are the results we got with different LLMs after fine-tuning with QLoRa. And from those results, we can see that from Mistral 7 billion base model, we outperform our baseline Gizmo model in terms of hit at 1 accuracy. Previously, the results were evaluated as 4-bit evaluation. That means when we get the results, we loaded the model in 4-bit. But when we loaded the model in 8-bit, we managed to improve our results and got around 22 accuracy. So as of now, our task is completed. Actually, we have outperform our baseline Gizmo model, but we tried with different techniques to further improve our results. So some of them are we fine-tune with another different parameter efficient fine-tuning techniques, and then two-stage fine-tuning. That means we first fine-tune the model with recipe details, and then as the second stage we found fine-tuning the model with substitution details. And multitask learning means fine-tuning the model with both recipe details and substitution details at once, and applying direct preference optimization. And also we have an idea performing full fine-tuning and pre-training also. It's a very huge task. We require massive hardware, but we have an idea of doing that also. So we only managed to do these techniques at the moment, and unfortunately we couldn't outperform our best results got from QLoRa with these results. So our idea is to improve these results further by applying full fine-tuning or pre-training, and also trying with these techniques also. So finally, as a result summary, as we got so far, we managed to outperform Mistral 7 billion, managed to outperform our Gizmo baseline model by using Mistral 7 billion model with basic fine-tuning with QLoRa and performing 8-bit evaluation. That is our main path, and we tried a different way also. That means in Gizmo they have used an ingredient vocabulary. So we thought of giving that ingredient list through the prompt to the LLM and ask for a substitute for that, ask for a substitute from that ingredient list. So we thought it would give us better results, but when we tried that, the issue was we couldn't give ingredient list such as including 6,000 ingredients through the prompt because of the limitation of the token limit in LLMs. So as a solution for that, we tried with rack pipeline. So we created a vector database including the embeddings of the ingredients in the ingredient list, and got the top K ingredients from that vector database according to the source ingredient, and give that top K, means some 200, we mainly focus on 200 ingredients, and we gave that 200 ingredients through the prompt to the LLM. So, but with that, the results we got from that was very low compared to the previous results, so we didn't go that way after that. That's also, we have a demo video. As the time being, I will skip that also. So here are the reference, and here are our team, and thank you all.
Any questions, audience?
So thank you very much for that insight into your work to try and outperform Gizmo. I noticed that with your model, you did much better with hits at 1, but fell off a little bit compared with Gizmo in terms of hits at 3 and hits at 10. Do you have any ideas why this might be?
Most probably because of the data set. In the data set, there is only one substitute for one ingredient in the recipe. So if we can modify the data set, including several substitute for one ingredient, we will manage to pass that hit at 3 and hit at 10 accuracy also. We think that's the issue in that.
All right, thank you very much.
Any other questions? Any other questions? No?
For the RAG retrieval, how did you do the retrieval? What were you matching?
That means the embeddings.
How did you get the embeddings? What models did you use?
There is a model called Foodbird. We first tried using that Foodbird model and got embeddings. And then we tried several sentence transformers in the Hugging Face also. And we tried different techniques to fine tune that sentence transformers, but from all those things, we couldn't pass 10. We only get about 80%, 9% accuracy. So that's how the transformers we use to get embeddings.
So the Footbird was the best one for them?
No, Footbird or no. There is a. You remember the sentence transformer?
Yeah, it was called multi-MPQNet sentence transformer. So like even from that we got like less accuracy. So we just had a better accuracy only just using the standalone like process we did before. So that's why actually we ignore the RAG process from
So you didn't do any embedding for the retrieval? For the
Sorry?
RAG retrieval, what kind of embedding did you use?
Yeah, we use the to check the similarity. We use cosine similarity.
What was the representation? Yeah, how did you form the vector?
Yeah, first we formed with Footbird
Ah,
model,
okay.
but it gave us very low results. So we tried with different sentence transformers in the Hugging Face. So we actually can't remember the name of that. We
Selected the best out of
yeah, we tried with several transformers and got the best one.
Okay, right, thank you.
Thank you very much.
Thank you, Ransika and Thevin. Our next presenter is Ishara Niranjana, paper ID 18, Assessing the Effectiveness and Challenges of RAG Applications, a Comprehensive Testing Framework. He is a machine learning engineer at Zone 24/7. Ishara, over to you.
Good afternoon. So today I am going to talk about the comprehensive testing framework for conversational AI applications. So I am Ishara Niranjan from Zone 24/7 and I am currently working as a machine learning engineer. So this is a work from our company. So we are actually in the industry for over 20 years and currently we are working as we are building software and hardware applications and embedded engineering applications, as well as machine learning, deep learning and generative AI applications. So this framework we are able to build from our experiences building with different conversational AI applications. So now first we look at what is retrieval augment generation. So we know from the morning we talked about different applications which are built from large language models. So today we are using large language models for every task and also these research areas as well. But we know that large language models are trained on historical data and these data will be in a specific point of time. So it doesn't know about new knowledge. And also there's a chance that these models can have cheated. So it doesn't know the exact answer, but from their general knowledge, it tends to give an answer. So in order to avoid these problems, we have a technique called retrieval augment generation. So it is like an open book approach for answering complex questions. So now we have different type of data sources like PDF, X files, and the data may be some data bases as well. So in order to implement these retrieval augment generation pipelines, we first need to import this data. So here we have data loading process, and then we need to split these data documents into chunks. So in order to do splitting, we can split these data into chunks as sentences, paragraphs, or in character level as well. And then we need to use an embedding model. So from this embedding model, so we need to represent these documents, text documents in numbers to use with different models. So in order to do that, we need an embedding model. And after that, for later retrieval, we need to store these embeddings. So we can use vector stores or graph stores for this one. So we can use these vector stores or graph stores in order to store these embeddings. So this is the first part of a retrieval augment generation application. So here we have this indexing pipeline. Then when user asks a question, there is a process. So this is the second part of this application pipeline. So this part is basically doing is what retrieving and generating an answer. So here, when a user asks a question, then this question is turned into an embedding, and then we need to check the semantic similarity of this embedding and the chunks. So then after that, this retriever will get the most relevant chunks for the question and generate these chunks and the user query to an LLM. So here we can use different LLMs. After that, the LLM will be generate answer from these retrieved chunks and the user query. So then user will get the final answer, which is more human-like nature. So this is what is happening inside retrieval augment generation. And so when we are building these things, we have seen that there are some areas that the answers might be incorrect according to the splittings and indexing errors and also retrieving errors. So we have identified that. So we need to evaluate these RAG applications in order to get an accurate answer. So if we look at why we need to evaluate these RAG applications, so we need to evaluate the text quality, diversity, and credibility. So when an LLM given an answer, we don't know that if it is trained on general data, the answer can be given from unauthoritative sources as well. So we need to check on the credibility. And then we need to compare different RAG techniques, models, and parameters. So if we look at this area, this is rapidly evolving, and due to that, there are different techniques evolving every day. So we need to evaluate our applications and improve over the time. If not, the answers and the accuracies will be low. And the next point is we need to identify retrieval and generation strength and weaknesses. So there may be some parts that retrievals are not accurate. So due to that, the answers are not the ones we are looking at. So the last point is we need to ensure user requirements are met and avoid harmful outputs. So now let's look at what are the components we need to evaluate in a RAG pipeline. So we have identified that there are main three components. The first one is the retrieval part, and the second part is the generation part, and another very important part is the performance. So this retrieval and generation are based on the quality of the response, and the performance is for the user experience on our applications. So this is the proposed testing framework according to our experience and the problems we faced during building these applications for conversational AI application. So here we have identified that these three main components, response, performance, and the retrieval part as knowledge augmentation. So in the response part, there may be some applications built on translations, summarization, classification, and question answering like generation tasks. So in the generation tasks, we have for the translation tasks, we can use Meteor scores, and for summarization, we can use ROGEL, and for general classification tasks, we can use accuracy, recall, precision, and F1 score. And for generation tasks, there are some parameters built from different companies as well as from the community. Those are faithfulness, answer relevance, repeatability, coherence, answer correctness, safety, and aspect ratio. So here, if we look at faithfulness, we are looking at the actual facts in the answer and how much amount of these facts are correct or not. And so in order to test these, we can use an LLM or these libraries, or we can use a manual approach as well. So if you look at the performance side, we have latency, number of requests per minute, and also the concurrent users, GPU performance. Likewise, we need to evaluate average context length and also the time to the first token rendering. So these parameters are very important, and we can create automated testing frameworks for checking these performance parameters. And then we have knowledge augmentation. So here, if we look at knowledge augmentation, we are mostly looking at the retrieval part. Here we need to check on context precision, context recall, and context relevancy. So we can use an LLM or manual approach for testing these applications on knowledge augmentations. So these are the main 3 parameters that we are going to evaluate from a RAG application. And if we can use this framework, we can build more valuable applications and accurate applications that are giving reliable responses. So if you look at the advantages of using a testing framework, so this will improve our accuracy and reliability, and it will improve the efficiency and development speed. So when you're talking about the industry and the rapidly evolving generative AI side, so we need to test these applications and need to evolve these applications with over time. And then we can improve the collaboration and maintainability of these applications. And the last point is we have that with these applications, we can, so with this increased collaboration and maintainability, this building these applications in a fast-paced environment is can be done efficiently. Thank you. So if you have any questions, you can ask.
Audience, questions?
Thank you. I have a question regarding the framework. I think for the response box, the rectangle, you had put an LLM as one of the approaches to establish the different metrics.
Yeah.
How practical is that? I mean, is it good to use another LLM to evaluate an existing LLM, and how do you?
Yeah, so we can use an LLM as a golden rule, like GPT-4 Turbo, some model that is performing better than the models we are using. For example, if you are using some local host models like Mistral or some 7 billion parameters models or some small language models, so we can use an OpenAI model for as the golden rule, and we can test over.
Do you see any problems in such an approach, or do you think, I'm just opening the question, because do you see that whether that might, there could be biases, there could be costs involved? I mean, how can everybody use the framework if you want them to use something like a GPT, ChatGPT type of thing?
So if we are using that LLM, we need to go for that one. But if there is a manual process as well. So all these parameters, we have defined functions. So according to these functions, we can test this manually as well. So in order to automate this process, we can use an LLM. If not, we can use manual.
So humans can sort of evaluate based on those metrics that you have specified. That is probably more transparent and fair, I would say.
So actually, we are using that approach for our applications most of the time.
Right. What kind of applications have you tested with your framework?
We have built a chat application for our websites. So we have tested with using this framework. So now if someone asks about the accuracy or some value, so we have some quantifiable values that we can give. So most of these parameters are given the values for 0 to 1 in the range. So we can give a number if someone asks for the accuracy.
Right. And the other things like faithfulness, and you had lots of metrics there.
Yeah, for all the ones we have that
Right.
function, we have functions.
Okay, right. Thank you.
Thank you very much for the talk. Quite interested in the sort of knowledge augmentation evaluation, because the purpose of a RAG system is that what you're retrieving means you're better able to generate some kind of response,
Yeah.
whether that response is more accurate or more faithful to your data, etc., etc. So I wonder, have you thought about other aspects of the knowledge augmentation that might be important to assess outside of the precision and the recall? Because I think there's a few opportunities there.
Yeah, in the indexing part, we have few opportunities. When we need to chunk these documents, we have to check that as well. So when we are checking on the retrieval, we are checking on the knowledge chunks as well. So if there's any problem, we can look at these problems and we can improve these parameters, like what is the chunk size we need to split these documents likewise. So in this retrieval part, we have the ability to check that as well.
Okay, thank you very much.
Thank you.
Yeah, actually from the industry, zone 25, yeah, right. Okay, thank you very much. Thank you. And our last session.
Thank you, Shara. And now for our last presenter for today, we have Chanuka R. Algama, paper ID 23, Conversational RAG with Memory-Based Content Enhancement. He's a junior researcher with Data, Algorithms and Policy team at LearnAsia. Chanuka, over to you.
A wonderful afternoon. I'm Chanuk Ravishan. This is an exploratory work I started a few months ago, and then it got developed to a conversational RAG, conversation query architecture. So let's first look at the structure of this presentation. So I'll first do building the storyline, and then I'll present the experimented solution, and then evaluations and future directions. So I'll start with a high-level overview. A fundamental feature of large language models is the ability to compress knowledge. The way this works is that you take a huge slice of world knowledge through documents, through books, and then you train a large language model using those knowledge. And what happens during the training process is that all the knowledge, all the concepts, all the theories, all the events that has happened in the world knowledge get compressed into the large language model. And essentially what happens there is that what you have done there is that you have compressed real world knowledge into a single large language model. And there are limitations when compressing knowledge. One is the knowledge is static, which means that it is not getting updated with new information coming. So you may have experienced this when you are using ChatGPT. And another one is like these models are trained on large, massive corpus of data, and resulting these models be good at general knowledge, but when it comes to specialized niche information, these language models falls apart. And another limitation is hallucination, and another one could be non-transparent reasoning. I think non-transparent generation could be a better word to use here, because we don't know whether language models do reason at all. Yeah, So to mitigate these limitations, we can use retrieved augmented generation, and this is where we augment the existing pre-trained large language model using specialized and domain-specific knowledge you have. And this comes in handy when you want to develop a chatbot to securely interact with your internal knowledge. And so talking about current RAG solutions, there are limitations in context capturing in follow-up queries. RAG fails miserably when applied in conversation settings. And there are also limitations in understanding complex queries and also accuracy in retrieval. And also when it comes to deployment solutions, there are no much deployment solutions rather than foundational RAG solutions such as LangChain, Llama Index. And if you have played around, you know that Llama Index is much more efficient than LangChain when it comes to large corpus of data. And also Llama Index chat queries most of the time fall apart when in the conversation settings. And when you're developing deployment solutions, most of the time you have the chain lead comes into rescue, but it is not much customizable. So this is an attempt to address the 4 limitations that we have discussed so far. In here, I'm presenting a conversational query architecture. I'm using Mistral 7 billion parameter model as the base model, especially in its 4-bit quantized version. And the superior performance of Mistral 7 billion was recognized when it outperforms all the 13 billion parameter models across all the benchmarks when the model was released. And the pipeline has 4 phases: indexing, retrieval generation, saving conversation history, and context enhancement, and also server-side and session-side management. So in the indexing phase, the primary goal is to get the documents, the data into manageable chunks. I'm using sentence window architecture, window parsing, and a one chunk contains 3 sentences. And I'm using Hugging Face BGE model, which is developed by Beijing Academy of Artificial Intelligence. And this is the embedding model that creates the numerical representations of the chunks, capturing its semantic meaning. And when configuring the model, I'm using the 4-bit quantized version, which reduces the memory usage of neural networks. And I'm using language temperature 0.1 because we need more deterministic answers and consistent answers. And max new tokens are 256. And context, I set the context window to 4K. And even though Mistral supports 8K context window, I set it to 4K to have some wiggle space. And even though Mistral uses some technique called sliding context window. And for building the core engine, I have used BGE, I have used a re-ranker model. So what is basically happening here is that when a search query is executed, engine will first retrieve the top K. I have set K to 6, and it will retrieve 6 similar items, and then it will update the relevant metadata. And finally, using this re-ranker model, I'm selecting the 2 best similar items. Then it passing to the language model. So in the third phase, I'm saving the conversation history to keep the track of the previous interactions, and And I have prompted our base model, Mistral 7 billion parameter our base model, to generate standalone questions while referring to the conversation history. So this is largely where the software engineering is happening, while saving conversation into memory, server-side management, and like formatting the memory when the session is ended. And front-end integration is HTML, JavaScript, and Flask, while backend is Python Flask application. Yeah. So talking about the evaluation metrics, there are evaluation metrics like generation, retrieval, indexing, and I'm currently in the integration, doing the integration of Ragas into this architecture because Ragas consume a lot of OpenAI tokens, so it's quite costly. And this is an evaluation of the developed query engine versus Llama Index, one of the built-in chat module. And we can see that the developed query engine has average correctness more than the Llama Index model. So talking about the computation requirements, it needs a minimal GPU of 12 GB and a 16 GB of RAM and a static IP address if you want to access this app through internet. And I have published the code base in my GitHub account. Thank you.
Questions?
I'll ask one and then pass. Thank you for the talk. I have a question about the retrieval. Am I correct that you said that there's a two-stage retrieval, that you first retrieve 6 and then you retrieve 2?
So I'm using a model there.
Yeah.
So it's a re-ranker model from Hugging Face. And what happens in that query engine is that first it will retrieve 6 similar items according to the query. And then using the model will re-rank the 6 items retrieved, and then I'm selecting top 2 ranking queries for the output.
So is there a way to do that without a double retrieval? Can you not just retrieve on one go and you have the rank list? Is there a reason for having it in 2 stages?
Yeah, so this is kind of advanced retrieval techniques like Llama Index, LangChain has some basic inbuilt modules, and they use the single retrieval process, but they are not much accurate when experimented. So by this, so what happens is like in the embedding space, similar items gets a proximity, but it doesn't mean it's accurate all the time.
Okay.
So we have to have a ranking to all the retrievers.
So the first one gives you a ranking, most similar 6 instances. Does it give you similarity to those 6 instances, or it just says these are the 6, you don't know in which order they appear? It gives a similarity score.
Yeah.
So could you use the similarity score to rank the 6 and therefore take the top 2 based on similarity?
Yeah, even though the similarity index is there, we can, there are some examples I can use, like if a query is asking the person's first name, but there are 2 people with person's first name and the second name, so we can use this ranking structure to get the best outcome.
So what I don't understand from the ranked 6 instances, what is it that you add onto that to get the best 2? What is the extra bit that you do there?
Using using a specialized ranking model, that model is specialized in ranking, comparing the query against the retrieved items.
Yeah.
Yeah.
whether you get the same result if you just took the top 6 and only took the top 2, rather than going through that extra process.
We could do that. Yeah.
Thank you very much for the talk. My question's more around the conversation history and how you're injecting it into the context window for RAG. So, conversations take place over multiple turns. So when you reach quite deep into a conversation, injecting the whole history can be quite costly or could potentially even get to the edge of your quite large token limit in longer formal dialogues like clinical dialogues. So are you using the whole history? Have you got some sort of short-term memory? What's going on there?
Yeah. So right now it's only referring to the last message, like when a new query is executed, it's only referring to the last message and get the context to the new message. Yeah.
Right. Thank you very much.
There's a problem in that because session is not handling pretty well because this is not in the production level yet. So this is using no-hop in Python. If you have worked with currently the management is done through the no-hop. So there are some integrations like limitations in managing the session. So session doesn't get terminated once the window is closed. So there's a path to work on. Yeah.
Any workarounds you have thought about to increase the performance?
Yeah, one is creating user accounts. So I could develop the front-end pipeline to have user accounts, and inside the user account you have a dedicated separate context. So that's one way to mitigate that problem.
Any more questions? Okay, thank you. I think that comes to the end of this session. So that is the end from this end, and then we break out to the main hall for the panel discussion. But we need to be sure whether they have finished. If not, we'll stay here and then go there. We'll have the panel discussion and then some awards, and that's it. Yeah, all right. So let's see.